Hey everyone, and welcome back to a brand new explainer. If you're in grade 12 right now, settle in, because today we are embarking on what I honestly like to call a mathematical detective story. We're going to solve the absolute mystery of functions that fundamentally break the rules, and we'll discover the brilliant loopholes mathematicians created just to tame them. We're tackling Chapter 2, Inverse Trigonometric Functions. So grab your notebooks, get focused, and let's unravel this whole thing together.
So check out this fantastic quote from the German mathematician Felix Klein. He said, "Mathematics in general is fundamentally the science of self-evident things." Now look, I completely get that when you're staring at a page full of inverse tangents and restricted domains, it might not feel super self-evident right away. But I promise you, by the end of our time today, the underlying logic we use to build these concepts is going to feel entirely clear, totally natural, and yeah, completely self-evident.
Okay, here's our quick roadmap for today. First, the inverse rule breakers, then restricting the domain, followed by mirroring the graphs. Next up is the principal value branches, and finally, solving for principal values. Let's jump right in.
Part 1. The inverse rule breakers. Here's exactly why standard trigonometric functions completely fail the test. Every good mathematical story needs a bit of conflict, right? Well, the villains of our story today are actually your old friends from Class 11, standard trigonometric functions, in their natural, unbound state. To understand why they fail, we have to look back at the inverse function golden rule from Chapter 1. Remember, an inverse function can only exist if the original function is strictly 1, 1, and on 2. Basically, what we call bijection. That means every single output must come from one and strictly one unique input. But think about a regular sine wave for a second. It just oscillates up and down, hitting the exact same y values over and over again out to infinity. Because it repeats, it wildly violates the 1-1 rule. So, over their natural domains, trigonometric functions simply cannot have inverses.
Which brings us to this massive, dramatic roadblock. How in the world do we invert the invertible? Because science and engineering absolutely desperately need inverse trigonometric functions for things like calculus and integrals. So how do mathematicians get around this fundamental rule?
That leads us nicely into Section 2, restricting the domain. This is basically the mathematical hack to force compliance.
All right, let's dive into this incredibly brilliant mathematical workaround, domain restriction. Take a look at the left. Notice that natural, endless sine wave for literally any y value, let's say 1/2. There are infinite x values that give you that exact result. But on the right, look what we've done. We've basically taken a pair of mathematical scissors and chopped the wave so we are only looking at the very specific interval from -π/2 to +π/2. By isolating just this dark portion of the curve, the function suddenly becomes strictly 1, 1, and on 2. It covers every single value from -1 to 1 exactly once. So by simply restricting the domain, we've magically created a pathway for an inverse to exist.
And hey, it's not just the sine function causing trouble here. Cosine, tangent, secant, cosecant, and cotangent are all periodic rule breakers too. To find their inverses, we literally have to apply this exact same logic. We must chop all of their domains into highly specific, non-repeating intervals where they behave perfectly and stay strictly bijective.
Section 3. Mirroring the graphs. Let's take a second to visualize this inverse relationship.
Now that we've kind of manipulated the algebra, let's actually look at the geometry. To graph an inverse, we use a really simple mechanical swap. If you have an invertible function y equals f of x and a point a, b lives on that graph, then the point b, a will absolutely, definitively live on the graph of its inverse. You are quite literally just taking the x and y axes and interchanging them.
And this visually illustrates exactly what that swap looks like on a coordinate plane. The graph of an inverse function is perfectly obtained by drawing a mirror reflection along that diagonal line y equals x. Notice the curve of the standard restricted sine function, and then just look at how it reflects right across that dotted diagonal line to create the really unique curve of the inverse sine function. It is a perfect geometrical mirror image.
Moving right along to Section 4, the principal value branches. Honestly, this is the holy grail of Chapter 2.
Okay, pay close attention because this is the absolute core of today's explainer. If there is literally one thing you remember for your final exams, it absolutely needs to be these values. These specific ranges aren't just random intervals somebody guessed. They are universally agreed upon by mathematicians all over the world. We call them the principal value branches. Let's walk through it.
For inverse sine, the domain is the closed interval from -1 to 1, and its principal value branch range is the closed interval from -π/2 to π/2. For inverse cosine, it's 0 to pi. Now notice inverse tangent right down there. It looks a lot like inverse sine's range, right? But it uses open parentheses. That means it doesn't actually include the endpoints -π/2 and π/2, because the original tangent function is undefined at those exact spots. Similarly, inverse secant and cosecant look like cosine and sine, but we actually mathematically subtract the exact points where they would cause a completely disastrous division by 0, like subtracting the set containing 0 for cosecant inverse. Seriously, memorize this table. It's your master key.
Now a quick warning. With great mathematical power comes great responsibility, especially when it comes to notation. Please don't fall into this common trap. That little -1 in sine inverse of x is not an exponent. It absolutely does not mean 1 over sine x. If you want to write 1 over sine x, you have to write it as sine x, all enclosed in parentheses, to the power of -1. Also, rule of thumb. Whenever a test question asks you to find the value of an inverse trig function and it doesn't specify a branch, you automatically always default to the principal value branch we just saw on that master table.
All right, the final stretch. Section 5, solving for principal values. Time to put all this theory into practice.
So we have the theory, we understand the restrictions, and we have the master table locked in our heads. It's time to roll up our sleeves and do some reverse engineering. Let's look at example 1. Find the principal value of inverse sine of 1/2. Step 1. Let's set the equation to y, so y equals inverse sine of 1/2. By the very definition of inverses, this algebraically means we are looking for an angle y where sine of y equals 1/2. Step 2. We immediately consult our mental master table. The principal value branch for inverse sine is the interval from -π/2 to π/2. Our answer absolutely has to fall into that specific window. Step 3. So what angle in that range actually gives a sine of 1/2? Well, you know your unit circle. It's π/4. Therefore, our principal value is just π/4. Boom! It really is that clean and logical.
Okay, let's level up just a bit with example 2, dealing with a slightly trickier negative value. Find the principal value of inverse cotangent of -1/√3. Step 1. Set y equals inverse cotangent of -1/√3. That basically means cotangent of y equals -1/√3. Step 2. We know from our basic trig that cotangent of π/3 is +1/√3. But because we need it to be negative, we have to use our quadrant rules. Negative cotangent of π/3 is the exact same as cotangent of the quantity π minus π/3. Which calculates right out to cotangent of 2π/3. Step 3, the ultimate reality check. Does 2π/3 fit into the principal value branch for inverse cotangent? The range is the open interval from 0 to pi. And yes, 2π/3 sits perfectly inside that window. So our final principal value is 2π/3.
And there you have it, folks. You've seen exactly how standard trigonometric functions break that golden 1-1 rule, and you've learned how mathematicians brilliantly restrict domains to basically force inverses to exist. Most importantly, you've armed yourself with the principal value branches to navigate literally any equation thrown your way. This foundation, it is going to be incredibly critical as you move forward. Because you know what's next up in your mathematical journey? Calculus is waiting. So the real question is, are you ready to use these brand new inverse functions to define and solve some seriously complex, mind-bending integrals? I absolutely know you are. Thanks so much for learning with me today, and I'll see you all in the next explainer.